This is a Module 5 continuous time Markov chain, lecture 3 Poisson process. In the first two lectures, we have discussed the continuous time Markov chain, definition, Kolmogorov differential equation, Chapman-Kolmogorov equations, and infinitesimal generator matrix. Then we have discussed some properties also. In the lecture 2, we have discussed the birth-death process and their properties, and also we have discussed the special cases of birth-death process, pure birth process and death process. In this lecture, we are going to discuss Poisson process and its application. So let me start with the Poisson process definition, then I give some properties in the Poisson process, and I also present some examples. Poisson process is a very important stochastic process. Whenever something happens in some random way, occurrence of some event, and if it satisfies a few properties, then we can model using a Poisson process. And the Poisson process has some important properties, whereas the other stochastic processes won't be satisfied with those properties. Therefore, the Poisson process is a very important stochastic process for the many modelings in applications like telecommunication or wireless networks or any computer systems or anything, any dynamical system in which the arrival comes in some pattern and satisfies a few properties. So before moving into the actual definition of Poisson process, I am going to give one simple example, and through this example I am going to relate the Poisson process definition. Then later I am going to solve the same example also. This is example number 2. Example 1 I have something else. Consider a car insurance claims reported to insurer. It need not be car insurance, you can think of any motor insurance or any particular type of vehicle or whatever it is. Assume that the average rate of occurrence of claims 10 per day. It is average rate per day, therefore it is a rate. Per day the average rate is 10. Also assume that this rate is a constant throughout the year and at different times of a day. So even though this quantity is an average quantity, there is a possibility someday there is no claim reported at all, or there are someday more than some 30-40 claims reported, and all the possibilities are there, but we make the assumption the average rate is a constant throughout the year at the different times of a day also. Further assume that in a sufficiently short time interval there can be at most one claim. Suppose you think of a very small interval of like 1 minute or 5 minutes or whatever, a very small quantity comparing to the, because here I have given the average rate is at 10 per day. Therefore, whatever the time you think of very negligible, in that the probability of or it is sufficiently small interval of time, there is a possibility of only maximum one claim can be reported. The question is, what is the probability that there are less than 2 claims reported on a given day? What is the probability that less than 2 claims reported means what is the probability that in a given day either no claim or one claim? Also we are asking the second question, what is the probability that the time until the next reported claim is less than 2 hours? Suppose some time one claim is reported, what is the probability that the next time is going to be reported before 2 hours? We started with this problem, the car insurance claims reported. Therefore, the claims is nothing but some event, and these events are occurring over the time. Suppose you make the assumption of sufficiently smaller interval of time, at most one climb can happen, and the average rate of occurrence of climb is a constant throughout the time. So, with this assumption, we can think of a sort of arrival process, a pure birth process satisfying some condition, and that may lead into Poisson process. So, this same example we are going to consider it again also. Now, I am going for derivation of a Poisson process, how one can derive the Poisson process. Poisson process is a stochastic process with some conditions. So, how one can derive the Poisson process? For that, let me start with the random variable n of t, that denotes the number of customers arriving during the interval 0 to time t. That means, how many arrivals takes place in the interval 0 to t. That means, for fixed t, n of t is a random variable. Over the time, this n of t collection, that is a stochastic process. I am making some 4 assumptions. With these assumptions, I am going to conclude the n of t is going to be a stochastic process. The first assumption, not x of 0, n of 0 is equal to 0. At time 0, the number of customers is 0, n of 0 is equal to 0, it is a wrong n of 0. Second one, the probability of arrival in an interval x to x plus delta t, that is lambda times delta t, where lambda is strictly greater than 0. That means probability that only one arrival is going to take place in an interval of delta t, that probability is lambda times delta t for a very small interval delta t. It is independent of x, that means it is increments are stationary, that property I am going to introduce in this assumption. The probability of more than one arrival in the interval x to x plus delta t is negligible. That means, at most maximum one arrival can occur in a very small interval of time, that is the assumption that I am specifying in third one. The fourth assumption, arrivals in non-overlapping intervals are independent. That means, if the arrival occurs in some interval and another some non-overlapping interval, then those arrivals are going to be from independent. That means, there is no dependency over the non-overlapping intervals arrivals going to occur or not. So, with these 4 assumptions, n of 0 is equal to 0 and the probability of one arrival is lambda times delta t in a small interval, more than one arrival occurrence in a interval delta t, where delta t is very small, that is that probability is negligible, and the non-overlapping intervals arrival are independent. So, with this derivation, I am going to find out the distribution of n of t. To find the distribution of n of t, first I am partitioning the interval 0 to t into n equal parts with the length t divided by n. The way I partition the interval 0 to t into n pieces, such that t by n is going to be a very small interval. So, that means, I have to partition that interval 0 to t in such a way that the t by n is going to be as small as. Therefore, I can use those assumption of a probability of occurring one arrival in that interval of length t by n, that probability is lambda times t by n, and the probability of not occurring event in that interval t by n is 1 minus lambda times t by n. So, I can use those concepts. For that I have to partition the interval 0 to t into n parts with a sufficient larger n, therefore, t by n is going to be smaller. Now, since I partition this interval into n pieces, n parts, I can think of at each parts I can think of a binomial or Bernoulli distribution at each pieces. Therefore, all the non-overlapping intervals occurrence are independent. Therefore, I can think of it is accumulation of n independent Bernoulli trials. Since it is a n independent Bernoulli trials for each intervals t by n of length t by n, therefore, the total number of event occur in the interval 0 to t by partitioning into n equal parts. This is a sort of what is the probability that k event occurs in the interval 0 to in the time duration 0 to t as n partition. So, out of n equal parts, what is the probability that k events occur in the interval 0 to t? That is nothing but, since it is each interval is going to form a Bernoulli distribution with the probability p is lambda times t by n. Therefore, the total number is going to be binomial distribution with the parameters n and p, where p is lambda times t by n. Therefore, this is the probability mass function of k event occurs out of n equal parts. Therefore, n c k lambda times t by n power k 1 minus lambda times t by n power n minus k. Now, the running index for k goes from 0 to n. That means there is a possibility no event takes place in the interval 0 to t, or maximum of n interval n event takes place in all n intervals. So, this is for a sufficiently large n such that the t by n is smaller. We take n tends to infinity to understand the limiting behavior of this scenario as the partition becomes final. Now, I can go for n tends to infinity. What will happen? As n tends to infinity, if you do the simplification here as n tends to infinity, that simplification I am not doing in this presentation. As the limit n tends to infinity, the whole thing will land up e power minus lambda t power k by k factorial. Now, the k running index is 0, 1, 2 and so on. This you can use the concept the binomial distribution as n tends to infinity and p tends to 0, your n into p becomes a lambda. So, that will give the Poisson distribution. The limiting case of a binomial distribution is a Poisson distribution. So, using that logic, this binomial distribution mass as n tends to infinity, this becomes a Poisson distribution mass function. So, this is nothing but the right hand side is the probability mass function for a Poisson distribution with the parameter lambda times t, and this is a random variable n of t for fixed t. Therefore, for fixed t, n of t is a Poisson distributed random variable with the parameter lambda times t, where lambda is greater than 0. Therefore, we can conclude the stochastic process related to the n of t for fixed t, n of t is a Poisson distribution. Therefore, the stochastic process n of t over the t greater than or equal to 0, that is nothing but a Poisson process. So, from the Poisson distribution we are getting Poisson process, because each random variable is a Poisson distributed with a parameter lambda times t. Therefore, that collection of random variable is a Poisson process with the parameter lambda t. Since it is a Poisson distributed random variable for fixed t, you can get the mean and variance and all other moments also by using the probability mass function of n of t. Formally, we define Poisson process as follows: a stochastic process n of t, t greater than or equal to 0 is said to be a Poisson process with the intensity or rate lambda greater than 0 if the following conditions are satisfied. First condition, it starts from 0, that is n of 0 is equal to 0. Second condition, The increments are stationary and independent. Stationarity means that for time points s and t, s greater than 0, the probability distribution of any increment n of s minus n of t depends only on the length s minus t of the time interval, and that the increments on equally long time intervals are identically distributed. Independent increments means that for any non overlapping intervals t comma s and u comma v, the random variables n of s minus n of t and n of v minus n of u are independent. For t greater than 0, n of t has a Poisson distributed random variable with the parameter lambda t. And the difference of the random variables defined over non overlapping intervals are independent. Lambda t is the cumulative rate till time t. The xi's are independent and identically distributed random variables with some distribution function g independent of the Poisson process n of t, t greater than or equal to 0. It is Markov in nature because the two queues act independently and are themselves a moment queuing system which satisfies the Markov property. Assuming that each queue behaves as the moment queue. That is all. एक और है सब. I do not know, I changed the word Poisson distribution into Poisson distributed random variable.
You have to say this sentence because QIJs are obtained by differentiating the PIJs.
I said.
No, you said that, but जो tone था ना, it was not with the full stop. It was as if you were going to continuation.
वो full stop है.
हाँ, वो full stop है.
ठीक है. एक और दबा, then you should remember that.
हाँ.
ठीक है सब. Yeah, the way I was, and similarly that n of t, can I tell again that Poisson? Okay. The details of the proof can be found in the reference books because QIJs are obtained by differentiating the PIJs. For every t greater than 0, n of t has a Poisson distribution with the parameter lambda t. Like that you can go for many more increments also. For illustration I have made it with the 2 increments. That means the occurrence of arrival during these non overlapping intervals are independent, and the stationary means it is a time invariant, only the length matters, not the actual time. Third one, for every t, n of t has a Poisson distribution with the parameter lambda t. So, the Poisson logic is coming into the fourth condition only. The first condition is start at 0, increments are stationary and increments are independent. The third condition, for fixed t, n of t is a Poisson distribution random variable with the parameter lambda t. Therefore, this stochastic process is called the Poisson process. Now, we can relate the way we have done the derivation. We have taken care these 3 assumptions starting at time 0, 0, increments are stationary, that we have taken, and increments are independent, that is non overlapping intervals are independent. Then when we have derived, we are getting the distribution of the random variable n of t is a Poisson distributed random variable. Therefore, this is a Poisson process. The another way of defining the Poisson process, we can start with the birth death process. You know that birth death process is a special case of a continuous time Markov chain. Also it is a special case of a it is a special case of a Markov process also. So you can think of a stochastic process, then the special case is a Markov process, then the special case is a continuous time Markov chain, then you have a special case that is a birth death process. So you can define the Poisson process from the birth death process also. A birth death process n of t is said to be a Poisson process with the intensity or rate lambda if birth rates are constant for all I and the death rates are 0. You start from the birth death process with all the birth rates are same, that means it is a special case of pure birth process in which birth rates are constant for all the states and the death rates are 0. Then also you will get the Poisson process. Here I am giving us a sample path for the Poisson process. So, this is created using the MATLAB. Write the simple code of Poisson process, then you develop the sample path. That means at time 0 the system at 0, at some time one arrival takes place, therefore the system land up 1, therefore the y axis is nothing but the n of t. So, at this time one arrival takes place, therefore the number of customers in the system, number of arrivals till this time, that is 1. So, it is a right continuous function, the value at that point and the right limit is same as, both are same, which is different from the left limit of the arrival epoch, arrival time of epoch. So, the system was in the state 1 till the next arrival takes place. So, suppose the arrival takes place here, then the n of t value is 2 at this time point in which the arrival epoch and the right limit and so on. So, this is the way, therefore, the system at any time it will be the same value or it will be incremented by only 1 unit. The Poisson process sample path will be with the 1 unit step increment at any time. There is no way the 2 steps the system can move forward. At even in a very small interval of time, the system will move into the only 1 step, that you can visualize here. Therefore, you can go back to the assumptions which we have started with the derivation, n of 0 is equal to 0. In a very small interval of time, at most 1 event can take place, and the difference of the random variables defined over non-overlapping intervals are independent, and increments are also stationary. So, those things you cannot able to visualize in the sample path. So, this is just one sample path over the time and n of t. The second one, inter-arrival times are independent. As well as we can conclude the inter-arrival times are exponentially distributed also. The inter-arrival times are independent and each follow exponential distribution with the parameter lambda. What is the meaning of inter-arrival times? At time 0, the system is in the state 0. First arrival occurs at this time point, second arrival occurs this time point, and fourth, third, fourth, and so on. The inter-arrival time means what is the time taken for the first arrival, then what is the interval of time taken for the first arrival to the second arrival, and second to the third, and so on. So, that is the inter-arrival time. So, whenever you have a Poisson process, that means the arrival of event occur over the time that follows a Poisson process, then this inter-arrival time, suppose I make it as a random variable capital T, and those random variables going to follow exponential distribution with the same parameter lambda, and all the inter-arrival times also independent. That means these are all identically distributed random variable. I can go for different random variable label also, x1, x2, x3, x4, and so on. So, all those random variables are IID random variables, and each follows exponential distribution with the parameter lambda. So, this can be proved easily. Let me start giving the proof for the first arrival time, that means the first one from 0 to the first arrival. Like that you can go for the other arrivals also using the other properties, or you can use the multidimensional random variable distribution concept and use the function of random variable, and you can get the distribution also. But here I am finding the distribution for the first arrival. So, let t denote the time of first arrival. My interest is to find out what is the distribution of capital T. I know that this is going to be a continuous random variable because it is a time. So, any time the first arrival can occur. So, to find, since it is a continuous random variable, I can find out the CDF of the random variable or complement CDF. So, here I am finding first the complement CDF, using that I am going to find out the distribution. Let me start with the probability that the first arrival is going to take place after time t. What is the meaning of that? The first arrival is going to occur after time small t. That means till time t there is no arrival. So, both the events are equivalent events. The probability of t greater than small t, that is same as the probability of n of t is equal to 0. That means no event takes place till time t, because the n of t denotes the number of arrival of customers during the interval 0 to small t, both are closed, 0 to 1, 0 to t. Therefore, n of t equal to 0, that means till time t nobody turned up, that is equivalent of the first arrival is going to take place after t. I do not know what is I do not know the distribution of capital T, but I know what is the probability of n of t equal to 0. Therefore, I am writing this relation. So, once I substitute the probability mass at 0 for the random variable n of t, just now we have proved that n of t for fixed t is a Poisson distribution random variable with a parameter lambda times t. Therefore, I know what is the probability mass at 0. So, substitute the probability mass function with the 0, I will get e power minus lambda t, that is the complement CDF of the random variable capital T. Once I know the complement CDF, I can find out the CDF. From the CDF, I can compare the CDF of some standard continuous random variable. I can conclude this is nothing but exponential distribution with the parameter lambda, because this is a complement CDF at time t. Therefore, it is a lambda times t. So, I conclude the distribution of a capital T is exponential distribution with the parameter lambda. That means, the first time of arrival, this random variable, that is a continuous random variable, and the continuous random variable follows exponential distribution with the parameter lambda. Since I know the increments are independent, increments are stationary and so on, I can use a similar logic for inter-arrival time of this time also, then that is also going to follow exponential distribution. Since the increments are independent, so this is the first time and this is second time, therefore, the inter-arrival time is also going to be independent. That means, whenever you have a Poisson process, that means the arrival occurs over the time in a very small interval, maximum one arrival takes place, and the probability of one arrival in that small interval is lambda times delta t. From that you will get the lambda. So, you can conclude that is a Poisson distribution, Poisson process. So, once the arrival follows a Poisson process, the inter-arrival times are exponential and independent. So, from the Poisson process one can get the inter-arrival times are exponential distribution and independent. The converse also true, that means if some arrival follows with the inter-arrival times exponential and exponential distribution and all the inter-arrival times are independent, then you can conclude the arrival process is going to form a Poisson process. That means arrival process, Poisson process implies the inter-arrival times are exponentially distributed and are independent. Similarly, inter-arrival times are independent as well as exponentially distributed with the parameter lambda, then the arrival process is a Poisson process with the parameter lambda with the intensity or rate. Now I am going for the stationary increment. The distribution of n of t minus s depends only on the length of the interval t minus s and does not depend on the value of s. That means during a interval delta t, the one arrival is going to be lambda times delta t, order of delta t, that will tends to 0 as delta t tends to 0. That means the stationary increments means if you find out the rate, that means you find out the average per unit of time, then that is going to be constant. So, this is the assumption we have taken it in the car insurance problem. The average rate per unit day, that is going to be constant, and that is the assumption we have taken it going to be a constant throughout the year and also the different times of a day. So, here also you will get whenever you have a Poisson process, then the average rate is going to be a constant because of the stationary increment. The next property, suppose you have a Poisson process of one arrival and you have a Poisson process of the other arrival. That means one type of arrival is a Poisson process with the parameter lambda 1 and another type of arrival that is also Poisson process with the parameter lambda 2. As long as both are independent, the arrivals are independent, then the together superposition, that is going to be again Poisson process with the parameter lambda 1 plus lambda 2. You can add the parameter. That means for fixed t, that is going to be a Poisson distributed random variable with the parameter lambda 1 plus lambda 2 times t. Whenever you have a two independent or more than one independent Poisson process arrival, then the merging or the superposition will be again Poisson process as long as they are mutually independent, with the parameter is nothing but the sum of those parameters. That is, you can combine you can combine many Poisson process streams into one stream, and that is going to be a Poisson stream with the parameter sum of parameters lambda 1 to lambda n. So, this is possible. This is used in many telecommunication application. That means suppose you have a Poisson arrival of packets from the different streams and all the streams are mutually independent, that arrival are independent, then the total number of packets are arriving into the particular switch or router, whatever it is, then the multiplexed one, that is going to be always a Poisson process. That arrival follows a Poisson process with the parameters or sum of parameter is nothing but the sum of these parameters, as long as they are Poisson as well as independent. The next property, decomposition. Suppose if you have one Poisson stream, you can decompose into many Poisson streams with the some proportion. So, that proportions are the P1, P2 and Pn's. So, one Poisson stream can be split into n Poisson streams with the parameter lambda times P1, lambda times P2, where each Pa's are greater than 0. The summation of Pa's has to be 1. That means that these are all the probabilities. With these probabilities, you can split one Poisson stream into many Poisson streams. So, here I have made a n Poisson streams. That means the same arrival is with some probability P1 it will end up here, with some probability P1 this put up here, with some probability Pn it is put up here. So, the split of one Poisson stream into n Poisson streams is allowed. That means the same example, if you have a one router, and from the router if the arrival is splitted into many streams with the probability P1 it goes to the first stream, with the probability P2 it goes to the second stream, and with the probability Pn it goes to the last stream, then each one is going to be a Poisson process. Each one is going to be a Poisson process with the parameter lambda times P1 and lambda times P2 and so on lambda times Pn. So, the split is possible as well as the superimposition is also possible from the Poisson process. So, this also has many more applications in the telecommunication networks. One type of packet arrival can be splitted into n proportions P1, P2, Pn's, and each one is going to be a Poisson process. Now, I am going to give the first example to illustrate the Poisson process. Consider the situation of waiting for a bus in a bus stand. Assume that the bus arrivals in minutes follow a Poisson process with the parameter phi, with the rate. The parameter here, that is nothing but the intensity or rate. Suppose you come to the bus stand at some time. What is the average waiting time to get the bus? When you land up a bus stand, there is a possibility the bus would have come before some time. The time in which the next bus is about to come, you are going to take that bus, and till that time you are going to wait in the bus stand, that is the waiting time. So, the waiting time is a random variable. So, that is a continuous random variable. The question is, what is the average waiting time? One can find out the distribution of the waiting time also. Here the question is, what is the average waiting time? So, what I can do, I can use the Poisson concept here. The arrival follows the arrival of a bus follows a Poisson process. Suppose at some time you come to the bus stand, and suppose the bus is going to come at this time, your waiting time is this much. So, suppose you make a W is going to be your waiting time. W is going to be your waiting time. The question is, what is the average waiting time? Just now I have explained the Poisson process as the property, the inter-arrival times are exponential distribution. The inter-arrival times are exponential distribution, and all the inter-arrival times are independent also. Therefore, this x1 and this is x2 and this is x3. So, x1, x2, x3, like that, so many all the inter-arrival times, that is going to follow exponential distribution with the parameter lambda. Since the waiting time is going to be the remaining time of arrival of the third bus. So, the W, the waiting time is same as the remaining or residual time of the third bus to come into the bus stand. So, x3 is exponential distribution with the parameter lambda. The residual lifetime of x3, suppose I make it as a notation x3 bar, the residual lifetime, residual time of arrival, not lifetime, residual arrival time of the third bus coming to the bus stand, that is also going to be exponential distribution. This is because of the memoryless property. The residual time is also, whenever some time is exponentially distributed, some random variable time is exponentially distributed, then the residual time is also going to be exponentially distributed using the memoryless property. Therefore, residual arrival time of a bus to come to the bus stand, that is also exponential distribution with the parameter same lambda. So, this is same as the W, the waiting time W is same as the residual time. Therefore, W is also going to be exponentially distributed with the parameter lambda. That means the waiting time for the bus to come to the bus stand to catch it. So, the W is exponentially distributed, therefore, the question is what is the average waiting time. So, average waiting time is nothing but 1 divided by the parameter, 1 divided by the parameter. So, here it says the Poisson process with the intensity 5, that rate is lambda, that is the mean inter-arrival time between the buses is 5 minutes. That means the mean inter-arrival time between the buses is 5 minutes is nothing but it is exponentially distributed with the parameter, that is average 5 minutes. Therefore, that is the same thing, therefore, that is equal to 5 minutes. Because the way I have given the clue, the mean interval between the buses is 5 minutes. That means the average of x is, that is equal to 5 minutes. So, that is the same as your waiting time, because it is exponential distribution, therefore, the residual is also exponential distribution, therefore, you can use the same value, therefore, the average is going to be 5 minutes. So, using Poisson process, one can find out the different results related to the number of arrivals. Next, I am going to give some more process related to the Poisson process. The first one is the non-homogeneous Poisson process. Let NT denote the number of customers arriving in the interval 0 to t. The arrival process has a Poisson distribution, but here the change, instead of the mean arrival rate is a constant, mean arrival rate is a constant lambda, but here it is a function of t. Lambda t is the cumulative rate till time t, that is a change from the Poisson process. Then this stochastic process is called a non-homogeneous Poisson process. Instead of a mean arrival rate is a constant, here the lambda t is a function of t, therefore, this stochastic process is called a non-homogeneous Poisson process. Second one, compound Poisson process. Using Poisson process, one can develop a little complicated stochastic process related to the arrival, that is called the compound Poisson process. Consider a Poisson process n of t, then you define a random variable xi, denote the number of customers arriving at the ith time point of arrival. X1 denotes how many arrivals takes place at the time of first arrival time point, and X2 will be what is the second time of arrival, how many arrival takes place. Therefore, I am making a new random variable x of t that involves t, that denotes the total number of customers arriving during the interval 0 to t. That means it is going to be how many arrival takes place in the first time point x1, how many arrival takes place at the second time of arrival, that is x2, and so on, plus x of t, x suffix nt. Here nt is a random variable, and how many arrival takes place, that is a x size. Altogether, that is going to be the total number of arrivals. The x size are independent and identically distributed random variables with some distribution function g independent of the Poisson process n of t. So, this is nothing but a random sum, because these are all the random variable, and how many random variables you are going to add, that depends on the value of n of t over the t. Therefore, this is a random sum of xi's with n of t. Obviously, these two are independent, xi's are independent of n of t, and since it is a number of our customers arrival during the in the ith time point, therefore, xi's are a discrete random variable, xi's are discrete random variable, and n of t is also Poisson process. Therefore, x of t is going to be a discrete state, continuous time, stochastic process, and we are using a Poisson process to get this stochastic process. Therefore, it is called a compound Poisson process. One can deduce a Poisson process from a compound Poisson process by substituting each xi takes a value only one unit. That means, the number of customers arriving at the ith time point is going to be only 1. That means, if I make a p probability of xi takes a value only 1, that probability is 1 for all I. Then I will have a only one value possible till n of t, then this is going to be a Poisson process. Suppose the probability of xi is suppose the xi's are going to be a discrete random variable with the possible values 0, 1, 2 and so on, then the x of t is going to be a Poisson process. I can make a simple sample path for the compound Poisson process. This is over the time and this is over the n x of t. Suppose these are all the time points in which arrival time point. So, this is the first arrival time point and this is the second arrival time point and this is the third arrival time point. It can be anywhere in the in a continuous time. Therefore, this is called a discrete state continuous time stochastic process. So, here I am relating with the random variable x1, this x2 random variable, this is x3. So, till the first arrival, till the first time of arrival, the number of customers in the system is 0. At the first time of arrival, the x1, suppose you think you make the assumption x1 takes a value 3, x1 takes a value 3. Therefore, this will be incremented by 3 till the second arrival. At the time of second arrival, suppose you assume that this takes a value 2 with some probability of x2 takes the value 2 is greater than 0. So, you have assumed value 2, it can take any other value also. So, it is incremented by 2 till it takes the third arrival, the value is so this is 0, this is 3, then 3 plus 2 5. At this time, whatever be the number of arrival, accordingly this can take some value. So, the difference between the compound Poisson process and the Poisson process, in the Poisson process the increment will be only 1 unit increment over the time, whenever the time at which the arrival time epochs, whereas here wherever the time of arrival time epochs, the number of customers entered, that need not be 1, it can be more than or equal to 1. So, that is the way the jump goes. Therefore, this is called the compound Poisson process. So, we have seen two variations of Poisson process, one is a non-homogeneous Poisson process, the other one is a compound Poisson process. So, before I go to the I complete, let me give the solution for the second example which I started. That is this question. The car insurance problem, we have discussed the two problems. The first problem is related to the bus stand bus arrival issues, and this is the car insurance problem. So, in this problem we have not assumed the Poisson process, but the problem is related to the Poisson process. One can assume it is a form of Poisson process, because you see the assumptions, the average rate of occurrence of claims is 10 per day, Also the rate is a constant, and in a very small interval of time at most one climb can happen. The questions are, what is the probability that there are less than 2 climbs reported on a given day? Since the increments are stationary, so any day you can think of with the only the interval. What is the probability that the time until the next reported climb is less than 2 hours? So, this is related to use the exponential distribution, because the inter-arrival times are exponential distribution. So, for the first question, you can assume that the n of t is nothing but a number of insurance car insurance claims reported to the insurer, that as a Poisson process. You can assume that n of t is a Poisson process based on the assumptions given in the problem. Once you assume that this is a Poisson process, the question is, what is the probability that there are less than 2 climbs reported on a given day? So, the given day 2 days you can shift into 0 to 2 days itself, because of the increments are stationary. So, the question is nothing but what is the probability that n of one is less than 2 in a given day, a day. So, what is the probability that n of 1 is a less than 2? That is nothing but what is the probability that n of 1 equal to 0 or n of 1 equal to 1. Therefore, the probability is added. So, you substitute since it is n of t is a Poisson process, the probability mass function of n of t is equal to k, that is e power minus lambda. Here the lambda is 10 per day, 10 times t, and 10 times t power k by k factorial. So, this is the probability mass function for the random variable n of t for fixed t. Therefore, n of 1 is equal to 0, that is nothing but e power minus 10. Here the t is 1 day, plus n of 1 is equal to 1, you substitute here, therefore, you will get 10 times e power minus 10. So, the answer is 11 times e power minus 10. Numerically you can get what is the value. So, the probability that there are 2 climbs reported on a given day is 11 times e power minus 10. The second question, what is the probability that time until the next reported climb is less than 2 hours? So, this is equivalent of the next reporting climb is less than 2 hours, that means the residual time of the next climb that is going to happen, the one climb is going to happen less than 2 hours. That means you can use the inter-arrival time, that is exponential distribution with the parameter lambda. Here the lambda is 10 or 10 by 2 hours, therefore, you should convert the values. So, it is 10 divided by 24. Climb can happen at any day throughout the 24 hours, therefore, 10 per day, therefore, it is 10 divided by 24 per hour. So, the t is exponentially distributed with the parameter 10 by 24. Now, the question is, what is the probability that the time until the next report climb is less than 2 hours? That means, what is the probability that t is less than 2? That is nothing but since it is exponential distribution and you know the CDF of the random variable t. So, the probability of t is less than 2 is nothing but 1 minus e power minus 2. So, 2 times, so 20 by 24. So, the answer is 1 minus e power minus 20 by 24, that is the probability that the next report climb is going to be occur before 2 hours. So, with this I have completed 2 examples also. So, in this lecture we have discussed Poisson process, and we have illustrated 2 examples for the Poisson process also. Some important properties also discussed in this. The next class I am going to discuss the applications of CTMC in queuing models. These are all the reference books. Thanks.